Good morning, everyone. Today we have came to attend the second day of online professional enhancement program on building a powered application using AWS. So yesterday we have seen the basics of AWS and how to do some of the basic practical exercise of EC2 instance, a virtual computer. We have seen that. Today we are going to see about some of the basic concept as well as the AI powered concepts. So okay, hope you will be enjoying the sessions. So now we can start the sessions.
So, hello all. A great good morning to all. So, yesterday we saw about AI, AWS basics about the AWS services and other applications. So, today we are about to see how to use AWS for building AI powered applications. So, let's start into the session. So, how smart is AI? Think about this. Modern large language models have read hundreds and millions of web pages, public books, research papers, and open source code repositories. You can ask them to write complex Python scripts, draft legal contracts, or pass bar exams, and they do it in seconds. Now, here's the problem. What happens when you ask that exact same cutting edge model a very simple question? What is our company's updated annual leave policy as of yesterday's afternoon? Or what is operating tolerance for motor B inside our private engineering manual? It fails. Of course, it confidently makes up an answer. Why? Because the model has never seen your private enterprise data. Welcome everyone. Today we are not talking about basic cloud computing or setting up EC2 instance. You already know AWS fundamentals. Today is the day we bridge the gap between massive public AI models and your understand organization's private data. By the end of today's session, you will be building a production grade retrieval augmented generation engine running live on AWS. So let's break down why this gap exists and look at the core problem every enterprise face when adopting AI. So look at what every organization is sitting on. You have standard operating procedures, HR policy PDFs, legal contracts, operational logs in database, and customer support tickets stored inside Amazon S3. This is your company's core knowledge. Now we have a challenge. We cannot send this sensitive proprietary data out to the public internet APIs to train public models like GPTs and Gemini. Security and compliance rules strictly forbid it. So we are left with a strict boundary. On one side, you have ultra intelligent AI models. On the other side, you have isolated enterprise data locked behind firewalls and S3 buckets. Our mission today is to build a secure, scalable bridge on AWS that connects these two worlds without compromising privacy or retraining massive models. To build that bridge effectively, let's step back for a moment and make sure we have a clear map of the AI technology landscape. So, when we look at AWS, it helps to separate your cloud stack into two clear operational layers. At the base, you have the infrastructure layer. This is cloud compute, network, security IAM policies, and basic S3 storage that you already know. Right above that sits the intelligent layer. This is where Amazon, Bedrock, S3 vectors, and knowledge bases. Think of it this way: infrastructure provides the raw compute power and durable storage, but the intelligence layer gives your application reasoning, search, and context. Today, we are shifting our engineering focus from managing virtual servers to wiring up managed intelligence pipelines. Before we touch the services, let's make sure we share the exact same technical definitions for the terms getting tossed around industry. So, the AI technology hierarchy. You hear terms like AI, machine learning, and generative AI used interchangeably all the time. Let's clean that up. So, artificial intelligence is a broad umbrella. Any technique that enables machine to mimic human intelligence. Machine learning is a subset of AI. Instead of writing explicit if-else code, we feed the machine historical data so it learns statistical patterns. Traditional ML is largely discriminated. It classifies existing data. Is this email spam or not spam? Is this transaction fraudulent? What is the probability of customer churn? It outputs a category of number. So generative AI sits inside ML, powered by foundation models. It is generative. It produces brand new content based on natural language form, whether that's raw text, source code, or vector representation. Now, how do these generative large language models actually process and generate text behind the scenes? So, today we are going to build the AI AWS paradigm. So, we are going to store our data in Amazon S3, which will be managed by Amazon Bedrock as a AI engine. So here's what where the model will be running. And for the vector database, we are going to use Amazon S3 vectors. Combining all of this, we'll have an enterprise RAG application in AWS. So let's understand the technology hierarchy of AI. So artificial intelligence is a broad umbrella of machine learning. Uh, all of the deep learning, machine learning, and generative AI comes under this artificial intelligence, where machine learning is a system that learns patterns from historical data, where generative AI and deep learning models are which that produce fresh text, code, images, and vectors, which generate some kind of content. So let's understand what makes this generative AI special. Normal ML models, they only identify the classifications and categories, whereas this generative AI has the ability to create something new, like a text, design, or images or audio. So, strip away the marketing hype and what is the large language model at its core. It's a massive probabilistic token predictor. A token is just a word fragment, roughly 4 characters of text. When you feed a prompt into an LLM, the model doesn't think like a human. It calculates probability distributions across its vocabulary and answers one fundamental question. Based on all the text I was trained on, plus the prompt provided, what is the single most statistically likely next step? It generates that token, appends it to the prompt, and runs the calculations again. It repeats this loop thousands of times per second. Keep this in mind because it is a statistical predictor trained on general web data. If it doesn't know an answer, it will still try to pick the most mathematically possible next token. That is how hallucinations happen. Transition. So, which brings us to the core engine powering modern generative AI, foundational model. So, what makes a model foundational model? Training a foundational model from scratch requires thousands of GPUs, terabytes of curated data, months of compute time, and tens of millions of dollars. Because of that cost, very few companies build them, like OpenAI, Grok, and Gemini from Google. As application developers and cloud engineers, we don't train foundational models. We consume them as managed services. Think of a foundation model as a pre-packaged engine. It arrives pre-trained on vast general knowledge. Our job as developers is not to rebuild anything. Our job is to steer it, give it the right data context, and build applications around it. And on AWS, primary place where we access these prepackaged engines is Amazon Bedrock. So, Amazon Bedrock is a fully managed serverless service that gives you single API access to high performing foundation models from top AI startups on Amazon. Here is why Amazon developers love Bedrock. First, zero infrastructure. You don't manage GPU clusters or EC2 compute nodes. You make an API call, you get a response. Second, strict data privacy. The prompt responses and internal data are encrypted at rest and in transit. Crucially, AWS guarantees that your data is never used to train the underlying base model. Third, built-in tooling. Bedrock isn't just an API endpoint. It natively integrates with the vector databases and data sources via Bedrock knowledge base. Bedrock doesn't restrict you to a single model either. You see what model choices you have inside the service. So, in software engineering, we don't use one single database for every task. We pick relational, key value, or document roles depending on the workload. The exact same rules apply to the foundational models in Bedrock. So, first, Amazon Titan. Excellent for high-speed text generation and generating vector embeddings. Anthropic Clause. Top-tier choice for deep reasoning, complex coding, multi-step analysis, and structured extraction. Meta Llama. Great open weights for option for synthetic data generation and low latency domain tasks. Fourier command and embed. Built specifically for enterprise search and multilingual ranking. Though Bedrock, you swap between these models through simply by changing a single model ID string parameter in your API request. So we have access to these world-class models. Now let's return to our original problem. How do we get these models to accurately answer questions about our private organization data? So why fine-tuning is not enough? Here's problem developers encounter. So, standard LLM response is like, what is our company refund policy for defective hardware? It just tells an answer. As a general rule, electronic refunds require a receipt within 3 days. It doesn't know the answer itself, but through RAG response, we get according to the policy doc from that particular document name. So with the section, hardware returns are processed within 90 days with instant RMA keys. So this is a grounded RAG response. This is how RAG works apart from the standard LLM. So here's the scenario: internal enterprise data. Now the real world enterprise challenges. An organization has 10,000 PDF documents containing customer records, engineering specs, compliance rules, and internal wiki stored in Amazon S3. So the goal here is to allow non-technical employees to ask natural language questions and receive instant verifiable answers by the citation from the documents. So here's the problem developers encounter. When people realize an off-the-shelf model doesn't know internal corporate data, their first instinct is often, let's fine-tune the LLM model on our PDF. Let's discuss why fine-tuning is usually the wrong approach for knowledge retrieval. Fine-tuning means taking an existing model and running additional training passes on your custom dataset. Cost and time. Fine-tuning requires specialized expertise, data preparation, and GPU compute time. So, the stale data. The moment you finish fine-tuning, your data changes. An updated HR policy or new engineering ticket forces you to rethink hallucinations and promises. Fine-tuning teaches a model state and format, not reliable facts. It cannot enforce access permissions on who gets to see what documents. Instead of retraining the engine, we use retrieval augmented generation. So here's right. Think of the different cycles. Fine-tuning is like telling a student to memorize 10,000 page text before entering an exam. Retrieval augmented generation or RAG is giving that student an open book exam. When a user asks a question, we don't expect the LLM to remember the answer from its internal weights. Instead, our system goes to the private database in S3, retrieves the exact two paragraphs related to the user's question, attaches those paragraphs directly into the prompt, and says, read this context, and answer the question based strictly on this information. This results in zero retraining cost, near real-time updates when S3 file changes, and exact source citations for every answer. Let's, let's break down the exact three-step mechanics of how RAG or let's walk through this process using a real-world example. Imagine your company has a PDF stored in S3 called Company Policy PDF. An employee types into your app, what is our annual leave policy? Here's what happens step by step. Our system takes the user prompt, searches our storage layer, and fetches the specific text chunk inside company policy.pdf that discuss annual leave. Augment. We assemble a new combined prompt payload behind the scenes. Context. Relieve, retrieve leave policy text chunk. So, question is, what is our annual leave policy? So, what it generated? We send this augmented prompt to the Bedrock Foundation model. The LLM synthesizes a clean, natural response, grounded strictly into the provided text. That sounds simple conceptually, but how do we prepare raw, unstructured PDF documents so a computer can instantly retrieve the right paragraph? So here's the document chunking strategy. What I say, here's the first data engineering step. You cannot pass a 500-page PDF file into an LLM prompt for every single query. Context windows are limited, long prompts increase costs, and passing irrelevant pages dilutes search accuracy. So we split or chunk our documents. We break documents down into smaller, searchable text segments. Common strategies include fixed size chunk strategy, sizing text into blocks of 300 to 1000 tokens with a small overlap, say 10%, so sentences spanning across chunk boundaries do not lose context. Hierarchical semantic chunking, breaking documents along structural markers like markdown subheadings, paragraphs, or technical sections. Once we have the text chunks, how do we search them? By meaning rather than just basic keyword matching. Here's the vector embedding. Imagine I give two sentences to computer. Sentence 1. How many vacation days do I get? Sentence 2. What is our annual leave allowance? Notice that these two sentences share almost zero matching keywords. Standard SQL queries or keyword searches would fail to connect them, but human beings know they mean the exact same thing. We need a way for a computer to represent semantic meaning numerically. That's what embedding helps us do. An embedding model, like Amazon Titan text embedding, takes a string of text and converts it into a long array of floating point numbers called vector. For example, 1024 dimensional vectors. Let's see what happens when we plot these vectors in a high dimensional mathematical space. This is where things get interesting. When text is converted into vectors, concept similarity turns into mathematical proximity. In a high dimensional vector space, vectors for terms like vacation days, annual leave, and time off request end up positioned right next to each other because these semantic meaning is close. Unrelated concepts like server margin migration or quarterly revenue are positioned far away in the vector space. When a user submits a query, we convert their query into a vector that calculates mathematical distance, such as cosine similarity. The document chunks whose vectors sit closest to the query vector represent our top search result. Now, let's look at how AWS organizes the physical storage for both your raw documents and these mathematical vectors. This is a vector similarity search. The user prompts, how do I request time off? Embedding model. This converts the query into a 1024 dimensional vector. So this finds the top key closest. So we need to distinguish between two storage responsibilities in our AWS pipeline. First, standard Amazon S3. This remains your primary object store. It holds the raw original documents, your PDFs, docs, images, and text files. S3 gives you durability, lifecycle management, and enterprise encryption. Second, Amazon S3 Vector. This is specialized vector storage capability built directly into the S3 ecosystem. It holds the numerical embeddings vectors generated from your document, along with the index pointers back to the original text in S3. It allows sub-second similarity lookups at scale. Managing document parsing, chunking, embedding generation, and vector indexing manually sounds like a lot of blue code. This is where Amazon Bedrock knowledge bases step in. Amazon Bedrock knowledge bases is a fully managed service that automates the entire end-to-end RAG pipeline. Instead of writing custom scripts to monitor S3, chunk text, invoke embeddings, APIs, and write to a vector database, Bedrock knowledge bases handles the full workflow of out of the box. It automatically fetches files from S3, parses them, splits them into optimal chunks, called calls Amazon Titan embeddings to generate vectors, and indexes those vectors into S3 vectors. So when a user comes in, knowledge bases executes the vector search, fetches the matching document and passes them straight to your designated foundation model. Let's trace this entire end-to-end architecture step by step. So you see how every component works. So here's the RAG architecture. Ingestion flow. Look at the screen. This is our data ingestion pipeline. We upload raw enterprise files like PDFs into our source Amazon S3 bucket. Amazon Bedrock knowledge bases detects new or updated files. Knowledge bases sends the text through its chunking engine to split the document into searchable keys. Each chunk is sent to the Titan embedding model, which returns high-dimensional numerical vectors. Those vectors and associated text metadata are indexed directly into Amazon S3 vectors. This ingestion pipeline runs seamlessly in the background whenever your enterprise documents are updated. Now that our documents are indexed, let's follow up the runtime query flow when a real user asks a question. Now follow the runtime arrow. The end user submits a natural language question through your app. The application routes the question to Bedrock knowledge bases. Knowledge bases converts the query into a vector and searches Amazon S3 vectors for the top matching document chunks. The retrieved context chunks are fetched from storage. The knowledge bases combines the retrieved context chunks with the user's original question into a single prompt payload. This payload is sent to the Bedrock Foundation model like Claude 3.5, Sonnet, or Amazon Nova. The foundation model generates an accurate answer backed by real document reference and sends it back to the user. Look at just what happened. The LLM produced an answer based on private data without that private data ever leaving your secure AWS boundary or being used to train a public model. We spent the last part of our session understanding how this entire system operates conceptually. Now we are going to talk about it. Let's build it. So let's move on to the hands-on training session. So now we'll see how to build a RAG on AWS and then use the Amazon Bedrock and Amazon S3 bucket as a vector here. So here I'm going to show you like how to construct a RAG using Amazon Bedrock, where we are going to use the latest Amazon S3 bucket data store. So first we'll move on to the Amazon Bedrock. Here, if you come down, there'll be a under the build section. You'll know there is a knowledge base. You click on the knowledge base. So what this knowledge base is used for? We can either create a knowledge base using a managed table with a native connector, passing all the vectors for it. So here's where all your data and other retrieved chunks are stored. So we create a managed table. So on creating the managed knowledge base, you'll get a random name here. If you want, you can change it. So there are additional configurations where you can put the description and the embedding models we spoke about. So we'll be using the managed embedding model, which is recommended. So this doesn't have the additional cost from the AWS side. We have the IA information on role-based management. So for data source, we are going to use Amazon S3 as we spoke. Instead of using Amazon S3, you can use either SharePoint, Confluence, Google Drive, OneDrive. Depends on your use case. Now we'll be using Amazon S3. Okay, so we'll be using this AWS account. We have to manage that also, as well as we need to create a S3 as well. So where we'll be putting the S3 buckets URL here. So we'll go to the S3. So we'll create a bucket. So hope you learned about S3 buckets yesterday itself. For now, we'll just create a bucket of general type, uh, and bucket namespace. All of these are is here. You can create a bucket name. We'll create the bucket name as AWS. Yeah, copy setting from the existing bucket. If you have an existing bucket, you can choose that existing bucket as well. So these are some of the ownership control. All of these are basics of AWS that we might have seen yesterday. So to go to the advanced setting, there will be object log. Now we'll just create a bucket. So this bucket name has already been taken. It seems. We'll try adding some number at the end, like 1, 2, 3, 4. So this is our bucket's name. Okay, hopefully our bucket has been created. This is our AWS bucket right now. But currently we don't have any data inside, right? So let's try updating some data set to it. What data shall we update? Let's update some CSV based data. Some we can get data set from Kaggle. So this is a marketing based data set on companies. It seems. Let's download this data set. Okay, I need to log in. Let me use my own account. So here's a sample CSV that we have, and we'll try downloading one particular data set with 1,000 records. So our data has been downloaded. Let's look at the data one. So so Here is the sample data set that we have with the index customer ID, first name, last name. So this data will be useful for us to do some analysis or something. Now we'll just load this data set into our console. Okay, we've uploaded our data set. If you want, you can upload any JSON based data, text based data, anything that you need to be uploaded. This is just a knowledge base. Okay. So now we'll move on to the knowledge base. Browse CS3 is uploaded. Upload has been succeeded. We have this customer data in our S3 bucket. To look at that, we will move on to the S3 once again. So this is our bucket's name. Inside our bucket, we have our data. So let's refresh it once. Okay, we've got our S3. We'll browse our S3. So our S3 bucket is visible here. Now we'll choose it. Our S3 bucket has been chosen. Now we'll move on to the create text. Knowledge base is getting created. We have configured our data source for now, but to configure data storage and processing, we'll soon get a pop-up window with the necessary embedding models. Let's wait for that. Yeah, creation of knowledge base is in progress. Okay, so it's getting created for now. Let's wait for it to get created completely. So meanwhile, let's see what we have done for now. So data format that was in CSV, we have uploaded it into the Bedrock as knowledge base. So the storage space is only consumed as a S3 bucket, but the important computational are done in the knowledge base. Okay, so we have thinking the data source right now. Now it's integrating it. Okay, the data source is yet to be synced. Until that, we'll wait. If you want, we can edit it. Now, I want the embedding models to be changed. Okay, for that, we'll once again do it from the start. I'll delete this. I'll be deleting this now. Let's create a new knowledge base. We'll delete it. So we'll give that knowledge base is deleted. We'll create a new KB with that existing S3. Specifically for content parsing and chunking, we have this. All the sync has been completed. So if you want, you can use the additional configurations. So there's advanced configuration, about the file size and how you want it to be. Okay. We create this knowledge base once again. So knowledge base is getting created once again. Okay. It's getting created. So this deletion of the existing has not been completed, and the creation of new knowledge base is also not in progress. Okay. Well, we look into the particular knowledge base. So we have the node. There is no data source here. Once it's created, and we'll connect it with the S3 in a second. But sometimes come a problem for us. Okay. So let's have a knowledge base history. So here we'll add the data source. Okay. Data source is syncing right now. Once it syncs, we'll use this data source. Also, we need to change the embedding model. For that, we'll use this AD. So Amazon CloudWatch is used for all the log-based systems where our computation logs will be shared here. We can use it to control the data. Okay, this S3 is getting synced. Meanwhile, we'll see what we have done until now. So we've went to the S3 bucket, and we went to the S3 bucket and created a bucket named AI knowledge base. Okay. And we are now laying the foundation for our RAG architecture. This S3 bucket is our source of truth. In production, this is where your PDFs, documents, or CSV would live before we ever touch another. We need a centralized version control location for the data we want the LLM to learn from. So even though S3 is a flat storage, we use folders to keep our ingestion pipeline organized. So we'll point our bedrock knowledge base to the specific S3 folder. That's what we've done. We reload it for data updation. So it has been synced already. Okay, so name is given. Still syncing. Okay, so we'll once again move on to the knowledge base section. It has not yet been deleted. Let's leave it. This is the created database, knowledge base. Now we'll have to change the embedding model. So editing this embedding model is not kind of possible because of some relevant issues, I guess. So we'll try creating another managed table. So we have stored the particular data type, content parsing and transform has been given. Here for the embedding models, instead of using managed embedding model, which is like default given by Amazon itself, we'll try using the um, model that we are choosing. We're going to use the Titan embedding model. Okay, like we're using this particular embedding model. If you go on the additional configuration, you can give any description if you want to. And all indexing is advanced indexing. We have given for all the types of documents, audio files, video files, and PPT, PDF documents. Every data will be extracted from all of these data formats. Here we will be needing to search for a vector store also. We'll search for a vector store where it is available. So the vector store. Okay, that is okay. Okay, we are creating this once again with the new embedding model. Okay. So why we use this particular embedding model is it will be of less cost. You don't have to like pay much cost for it. They are giving some free credits for using this particular Amazon's embedding model. If you are using any other model from external source like Cohere or OpenAI, then it might cost you some more. Okay, let's wait until this is created. Until that, we'll look at some of the new features of S3. So S3 we got vector buckets also. So let me like tell you a bit about vector bucket. So how this vector bucket is used for us? We are going to um, use this data to be stored as a chunk in this knowledge base. Okay. So once the data is stored as chunks, they are like put into a vectors. They are converted into a vector embedding and it will be stored again on the S3, but in the vector buckets. So why we use this vector bucket? It's for semantic understanding. Um, we'll, we have already seen about the semantic understanding. Now we'll test the knowledge base. Okay, first. So you can write a prompt and search about the results. So first that before that we'll configure the APIs on agent uh, retrieval and response generation. So we have agentic retrieval with answer generation, agentic retrieval only, standard retrieval only. So there are like multiple options where like standard retrieval is like it will only be fetching results from one particular KB. Okay, you have multiple knowledge bases, but it will only fetch from a single KB which it is defined on. So agentic retrieval. So agentic retrieval is where it retrieves the data from our system through an intelligent multi-source retrieval. Like it won't generate a synthesized response. It will generate a creative response. And agentic retrieval with answer generation. So answer generation is where you use the retrieved chunks and pass it on again to the LLM and make it more summarized for your better understanding. So right now we'll keep the agentic retrieval with the answers generation. And here you can choose the models we've discussed about. You can now choose the Amazon model itself. You don't need to very high model. So we'll now go with the text model of 128 uh, 1,28,000 A tokens. Okay, apply. So the knowledge base source chunks. So what this means is only 5 chunks from our knowledge base are retrieved and they are augmented and generated. You can choose the number of chunks that you want to be present here. Okay, so now we'll test this model. Before that, we'll look into our data. So in our data, let's ask. So let's ask about nickel cannon. Tell me about nickel cannon. I'm not sure if this is going to give us the exact data, but let's see. Okay, there's some error. Tell me about the data. Okay, we have got some API error here. Hmm, let's see. Is there any issue with the knowledge base? Let's see if there is any issue with it. Okay, we'll go straight for testing it. Here, we'll give standard retrieval only, and with that, we'll use the model as Amazon's 300K tokens model. Okay, here is routing instructions. So if you want a particular type of data only to be given, then you can type here, say the context engineering. Let's give specific data about it. What's the email of nickel cannon? Okay, so there's a particular error with our model. Let's sort it out. Data is present here. Vector buckets is also present here. Or else simple, we'll try creating another model itself. It's not a big issue. So start. So here in the additional configurations, we'll use the Bedrock embedding model with Titan's X model. Right. So data source is also given. We'll use this particular data source. So for the data source, no additional configurations for now. The content parsing and chunking, we use the default chunking prefix pattern. You don't need any prefix pattern, I believe. In the advanced configuration, we have the content indexing to create knowledge base once again. Still getting created. Just wait until this is created. So let it get created. Until that, we'll proceed with our how and what we have done here. So let's try to have a overall understanding here. Okay, first we created an S3 bucket, which is like to store our company data and all the types of data here. And then we created a S3 vector bucket. So vector bucket is where our vector embeddings go, right? And we use the Bedrock, Amazon Bedrock knowledge base to create a knowledge base. Then we point it on to the vector bucket, uh, S3 bucket, and then we click sync. So now we are on the testing phase. Once this is created, the knowledge base is created. Fail to create. Okay. We need to specify some roles for creating this particular embedding model. Okay. So we'll create some roles. Create an existing role. Okay. 1, 2, 3, 4. Fix pattern. Okay. Now we'll try creating knowledge base again. That was an error here. We can't choose this particular embedding model without giving a particular role. So we found the error. Now we'll proceed with the creation of knowledge base. One before this is created, we'll have a case study. Okay, here's a scenario. You are hired by a manufacturing facility and field technicians servicing complex machinery currently spend 40% of their day digging through physical binders and thousands of pages of PDF repair manuals stored on the shared devices. They need a voice enabled mobile assistant that lets a technician ask How do I recalibrate policy on model 400 and instantly get precise procedure? So think about this. Based on what we built today, what AWS architecture would you design to solve this? Let me give you a uh, one solution of AWS. The mobile app captures the technician's audio, converts it into a text, and calls an API gateway endpoint backed by AWS Lambda. Lambda queries Bedrock knowledge bases, which retrieves relevant manual sections from S3 vectors. Plant processes the exact technical step and returns step-by-step repair guide directly to the technician's phone. One more case study is a major university receives thousands of repetitive student inquiry every semester regarding course housing deadlines and international visa complaints. Administrative staff are completely overwhelmed. What AWS architecture do you deploy here? So here's the solution. All official campus handbooks, course catalogs, and complaints PDFs live in an S3 bucket. Amazon Bedrock Knowledge Bases indexes those documents into S3 vectors. A lightweight web chatbot running on the student portal queries the knowledge base in real time. Students get 24/7 instant answers with direct links to official campus policy pages and administrative support tickets drop over by 60%. So let's summarize the core technical lessons we've learned today. So keep these three core principles in mind whenever you design enterprise AI systems on AWS. So you need a private data first. Do not jump straight to the expensive model fine tuning. RAG allows you to ground for foundational models in your enterprise data while maintaining strictly privacy and zero retraining overhead. S3 vector efficiency. Purpose-built vector storage in S3 handles high-scale similarity search natively at significantly lower operational cost. Serverless speed. Amazon Bedrock knowledge bases remove complex blue code, turning ingestion, vector search, and context augmentation into a managed pipeline. So think about how much the landscape has shifted. Yesterday, AI was something you used. You just opened a web browser, opened ChatGPT, typed a prompt into a public endpoint, and copied the output. Today, AI is something you build. When you combine the cloud infrastructure, private enterprise data, high-dimensional vectors, and managed foundation models, you aren't just calling an API. You are building an intelligent application that solves real operational problems. You now have the full architectural blueprint and practical hands-on experience running live on AWS. So I suggest you build something useful with all these available resources. Let's see if it is created. Okay, you are unable to verify this. Let's try with the existing model itself. Manage vector search. We'll test it. We'll use the managed model itself. That way you'll be able to watch. It is giving us the okay, got it. It is giving us the correct email. So let's see what chunks it used. Nice. One second. We'll move this away. So this is the chunking I spoke about. So the chunk text, all the index, customer ID, first name, last name, all from our data has been taken here. Okay. Then metadata associated with chunk. It has created a metadata itself, what the file type was and the document ID, from where it has taken the data. All of these are taken. So here's a trace details. Trace is nothing but how the chunks are being traced. There is chunk 1, chunk 2, chunk 3, chunk 4. All the similar 5, I mean, we have given the number only 5. If we are giving 6 or 7, let's try giving 3 chunks for now, for the next test. So let's try giving something bigger. All of the different companies are here, or else we'll try um, uploading another document itself. That way you would know better understand something. We'll try uploading a PDF document about a story. So, or we'll try yes, uh, story PDF for LLM fine tuning. Okay. So this is a nice story of 5 pages. We have this. This looks like a research paper. We'll download this research paper now. Store it in our S3 bucket. Okay, our PDF is stored now in our S3 bucket. We'll upload it. Getting uploaded. Upload has been succeeded. So, okay, so we have 2 files right now. We'll leave this alone. We'll refresh it. So it will be synced here. Okay. Now we'll give only 3 chunks. 3 chunks, and we'll be looking at the data from this PDF. Let's ask some questions related to this PDF. Let's ask the above itself. We'll ask about the fine tuning approach in the LLM fine tuning. Tell me about the fine tuning approach in LLM fine tuning. So it has given. I don't have information about LLM fine tuning approaches in the available knowledge base. The documents I have, which is unrelated to you. Okay. Our data has not been synced. Okay. We'll try syncing it first and then we'll browse S3 once again. Uh, It is getting synced now. Once this is synced to our knowledge base, then we can ask questions regarding this PDF to our model. Or else better, we'll create another S3 bucket itself. So I have created in the previous bucket, there was two types of data. One was of CSV type and one was of PDF type. That might be a problem for us, problem for our model to understand about it. So better we create the PDF AI 1, 2, 3, 4. We'll create this bucket. Upload the PDF file that we had downloaded. Okay, upload. In the knowledge base itself, instead of using this, okay, this file has been uploaded. In the knowledge base, instead of using the previous S3 bucket, we'll use the new S3 bucket. It has also been synced. We'll try it once. If it doesn't work, we'll move on to the standard. Tell me about fine tuning in uh, LLM fine tuning. Okay, Python query iteration. It's thinking about it. The model is kind of working. Okay, it has given all the answers. We'll look at it. Fine tuning in LLM code. So it has collected the data from this PDF, LLM fine tuning approach. Then it has passed on, retrieved that data, and augmented it using LLM, which is the model equivalent to Claude Sonnet. It will manage on its own since we haven't specified a particular model. So that model has returned the context right now. So it's not possible to see here properly without a full interface. So this is what the answer that is given by the our AI that we built right now. Let's look at the backend process of this. So proceedings of the 17th International Natural Language Generation Conference. So it has read every little chunks from this uh, PDF, and then it chose to search from each chunk one by one. Okay, so around 15 chunks has been chosen. So we have like 15 chunks from this particular PDF itself. From that, the trace, only 5 chunks has been selected. From the 15 chunks, we choose only 5 chunks. Now let's reduce the number of chunks into 3. Let's ask one more question. Epoch testing. Tell me about epoch testing. So now only 3 chunks should be chosen. This will increase the accuracy of the answer that is being given. But we should not reduce the number of chunks also. which will lead to improper generation of the context. So now another answer is also generated. Okay, epoch searching is here. Let's copy and paste it, see what it's given. Epoch searching, it has given the, uh, it has retrieved the data and it has given a much better answer from the PDF, I guess. So let's see the trace details now. So again from the 14 chunks, 3 chunks have been chosen. So this is how the data has been collected from the knowledge from the vector database, and then it is passed on to the knowledge base. Then in the knowledge base, the Amazon Bedrock runs a ML model or AI model, and then gives us the answer. So this is all the session about. I would suggest you to try similar projects and hope you build more relevant use cases also. So thank you all. Thank you for the session and
So thanks for
there
the participation. So if mic is now enabled and you can chat, if you have any questions, you can ask in the group. So ask in the chat, or otherwise you can unmute yourself and you can ask the questions.
so there are some questions in the chat box. I'll proceed with it. First, Haridarsani has asked, sir, then cloud computing is the basic to learn applications of AI. No, cloud computing is a different field. AI is a different field. So you're just starting to like build AI powered application, then hosting it on a like some cloud like AWS or GCP or Azure, so that it can be used in real time. That's the main concept of it. Any more questions? And Pratiksha has, can one S3 bucket store different types of files? Of course, yes. So one S3 bucket is just a storage space where you can store any number of files of any type. Um, any more questions, please? So Mohammed Niaz has asked, okay, is it possible to use all the files? Mohammed Niaz has asked, yes, it is possible to use every file like CSV, PDF, documents, Word documents, um, PPTs, everything can be uploaded. Pratiksha has asked, which Amazon Bedrock feature is the most useful for developing a college level AI? So um, as for now, this knowledge base is the actually you cannot ask this question. Think of it like this: Amazon Bedrock is just one part of the AWS service. Here you can just use to run the model, but you obviously need other instances like S3 and EC2 and like DynamoDB. No, we haven't used DynamoDB or RDF here. Those are used to store the data and manage a big database. We haven't like tried using it. You can try using that services as well. Okay. Any more questions? Haridarshini has asked, then cloud computing is one of the tools to apply. Yes, exactly. So you can apply full stack development in AI. I mean, sorry, full stack development in cloud computing, cyber security in cloud computing. All of these, like, there are multiple domains. So each of these has to be put in somewhere, deployed somewhere. So that deploying part is where cloud computing is used. Okay. So any more questions?
Wind up the sessions. So thanks for the participations. Dear participant, thanks for the participations.
Thank you all.
Yes, thanks for the participation. So all of them be in the group, active in the group. We will be posting many workshops related to AI, so related to technologies. So frequently, weekly, Sunday, 11 a.m. to 12:30, we will be frequently organizing workshops and many activities. Kindly be participated and in our program. Once again, thanks for the being participation. Today evening, you will be receiving your e-certificate for this